This video is going to cover centering and scaling, which are ways to make the coefficient of an explanatory variable in the model or an intercept more interpretable. So say we're looking at the influence of height on weight, and height's measured in millimeters and weight's measured in pounds. So it's a continuous outcome and a continuous predictor. This intercept here represents the baseline weight when height is 0, and the coefficient for height here represents the increase in weight that accompanies every 1 millimeter increase in height. And that's because height is measured in millimeters, so because beta is always a 1 unit increase, it's a 1 millimeter increase in height. There's some problems with this. The first is, what does a height of 0 really mean? And also, would the weight change meaningfully over 1 millimeter? Scaling lets us solve both those problems by choosing a more realistic baseline than 0 millimeters, and also picking a more reasonable 1 unit increase than 1 millimeter. So just some review on the linear equation y equals mx plus b. Y is the position of the line on relative to this axis, and x is the position of the line relative to this axis, this x-axis. And b here is the intercept, 3 in this case, and m is the slope, so rise over run, so 2 over 2 comes out to 1. So this equation, or sorry, this line is described by y equals 1x plus 3, where if we were to plug, say, 2 in there, we'd have 2 plus 3, so 5. And so when x is 2, y should be 5, and we see that that's true. For our weight-height relationship, that you can also describe it similarly with y equals mx plus, or sorry, y equals mx plus b, where now b just comes first, basically. And say we get our equation for the relationship between weight and height is 10 plus 0.1 x for height. So that means that the baseline weight here is 10 pounds, and a 0.1 pound increase for each 1 millimeter increase in height. And that line is really small. It's got a low intercept, a weight of a baseline weight of 10, which is low, and also it's only increasing at very small increments. So our baseline weight is 10, and that's when height is 0, which is an unreasonably small baseline height. And also when weight is increasing by 1 millimeter, which is very small increases. It's very small increments that it's increasing by. So say we thought that a 5 centimeter increase was a more reasonable increase than 1 millimeter units. We take this coefficient, it's 0.1 pounds per 1 millimeter, and the reason it's that is because it's this coefficient's 0.1, and that means that for every 0.1 increase, for every 1 millimeter increase, there is a 0.1 increase in weight, so 0.1 pounds per 1 millimeter. We know that 50 millimeters are present in 5 centimeters. What we ultimately want our x-axis to be going up by 5 centimeter increments. We can multiply across and cancel out these millimeters, and we end up with 5 pounds per 5 centimeters. So 0.1 times 50, that comes out to 5, and we're keeping the 5 centimeters here because we don't want it in 1 centimeter increments, we want it in 5 centimeter increments. I initially had it in 1 centimeter increments, but that didn't have a meaningful change compared to what we had initially. So like this really shallow line, a 1 centimeter increment wasn't enough, basically. So now our coefficient has a different meaning. It changed a little bit. Weight equals 10 plus 5x. So now this coefficient is it's now a 5 pound increase per 5 centimeter increase in height. And you'll notice here that the x-axis is in increments of 5 centimeters. So although it's going up like 5, 10, 15, 20, it's each unit here represents 5 centimeters. So this 10 here is 10 5 centimeter increments, which represents 50 centimeters. And this is our line now. Our line went from being really shallow to going up by a lot, and basically that makes sense, and that's because now every unit is a significantly larger increase in height, which you can anticipate will be a much bigger increase in weight. And what we do to the actual data in order to achieve this is, say we have this data, we have 3 observations, and we have the people's height in millimeters. For this first person, we can go from millimeters to the 5 centimeter units by knowing that 1700 millimeters and multiplying by 5 centimeters per 50 millimeters. The reason we're doing that is because that permits millimeters to cancel, and you're left with centimeters. And the reason we can just multiply by this is because this is equivalent to 1, basically, because 5 centimeters is equal to 50 millimeters. So that'll come out to 1, and that's just a trick you can do to change the units of whatever you're looking at. So basically, we're just dividing by 50 millimeters, and we have 34 units of 5 centimeters, so 34 5 centimeter units. So by just dividing each of these by 50, we were able to get it into the 5 centimeter units. So what changed? The coefficient of height changed. It went from 0.1 to 5, and before it was for every 1 millimeter increase, the change in weight. Now it's the change in weight per 5 centimeter increase in height. The significance of this would stay the same. Say it was significant, like a value of like 0.01, it would be the exact same, because the relationship hasn't changed. We just changed the units, basically, that it's occurring over. The intercept also stayed the same. It's still 10. But what if we think that 10 isn't a reasonable baseline? What if we think that, what if we know that right now 10 is the weight when height is 0. But what if we think that a height of 0 isn't reasonable, but a more reasonable lowest possible value be 140 centimeters? We can make that the new, basically the new intercept by putting that into the units of 5 centimeter increments, because the rest of our equation is in that. So 140 centimeters divided by 5 centimeters, so at 28 units of 5 centimeters. And now basically what we can do is we know that 28 is where we want our new intercept to be. So basically we want this now to be the y-intercept. And something I'm going to do just to kind of show like conceptually what's happening is basically this. We're physically moving the line over until that is the new intercept. So now it intersects with the line at 150 pounds. Yeah, and that's something we're able to do. And so when I move that over, you can see it comes out to about around 150, and we can see if that's the case by basically plugging this value of 28 into the equation, because this equation is describing this line. If we know the x value is 28, we can get the y value. So it comes out to 150, so that gives us an indication that we're making the right decision. So now our equation is weight equals 150 plus 5x. And the way we can alter our data, you'll remember our when I go back far enough, our data that we're left with is here. We have this 34, 32, and 36. And if we go back to where we were, to do this, basically conceptually, remember how we dragged it from here to here. That's basically what we're also doing to each data point. We're just subtracting 28. So now 28 is the new 0, basically. And yeah, when we subtract that, we end up with our height data looking like this. And it's been transformed twice. It's been put into 5 centimeter increments and also rescaled, so it's new 0 is 28. Centering is the next thing I'm going to talk about. Centering is kind of similar to what we were talking about before, but it's basically we decided to choose 28, which corresponds to 140 centimeters, based on that just being a value we feel is the lowest possible value. Centering is subtracting the mean value, so we have our observations here. We have the 5 observations, their weight, and their height. Centering is taking each of these values and subtracting the mean of the height data. So the first step is finding that mean. So let's say the mean is 168. Then for each value, we subtract 168 from it, and we get a new set of data. And now, basically, like we've subtracted the mean from it, so now the intercept is the mean value, and each of these terms are the position of their original data relative to the mean, basically. So another useful reason to center is basically to take care of collinearity. And collinearity is an issue that deserves a video of its own, but basically it occurs when, like, our model here would be weight is the outcome and height squared. The reason we might include height squared in addition to height is if height had a non-linear relationship, so if it looked quadratic, including a quadratic term might account for that. But this introduces an issue of collinearity, where collinearity is the idea that these two are contributing the exact same information, and or at least one is a function of the other, and that's exactly what's happening here, almost perfectly, in the sense that every value of height squared corresponds to it's a function of its corresponding value of height, so it's just height squared. And if we center, we can help reduce the influence of this collinearity. So we do that like before, just subtracting the mean value from each height observation, and also subtracting the mean value from each height observation and then squaring it to get the new height squared variable. And if we input this data, it's likely going to suffer from less collinearity issues. Standardizing is the very last thing I'm going to talk about, and it's kind of doing both an absolute scaling, so subtracting the mean, but also a multiplicative scaling, in the sense that for each height value, you're subtracting the mean height value and dividing by the standard deviation of the height data.